So today the problem that we're going to solve involves finding all of the optimal parameters so that we can make a spring that carries the amount of energy that we need to drive a cart up to a certain speed. This is a different kind of problem than some of the others that we have worked up till now, because we are not going to constrain ourselves to just discrete wire diameters for the spring. We're going to allow these diameters to range over a continuous domain. And so we're also going to let all the other parameters range over a continuous domain. This is a relatively tricky problem, but we do have the ability to use a piece of software, Microsoft Excel, and it makes our life a whole lot easier because it has this really nice feature built into it called a solver. So that's what we're going to do today. So let's get into the problem. So the first thing you see here is that we have a cart that is being driven by a spring, by basically the spring pushing on this rack, which meshes with the pinion. That will make the wheels turn, and so you should be able to pull it back, which will wind up the spring, and then let it go, and then that'll push it forward and it'll attain some maximum speed. It says here that the overall weight of the cart is 8 pounds. The front axle assembly weighs 2 pounds and has a radius of gyration of 3 inches. We'll get into why that's important here in just a second. We're also going to assume rotational inertia for this back wheel is negligible and that there aren't any friction losses. The wheels here have 5-inch radius, and they're going to roll without slip. It has to be able to attain 12 feet per second, and we need to design a steel spring that's going to limit us to a few different options. Essentially, that's going to be a hard-drawn spring, or an oil-quenched spring, or a music wire kind of spring if we want something that's more of a plain kind of a steel, which is, we're going to limit ourselves to that for just now. Kind of to limit the amount of work we got to do for this problem, and that should be helpful. We want to design the lowest possible cost spring using the text recommended guidelines for solid safety, fractional over under closure, and absolute buckling stability. So this is what our task is. Very first thing to kind of note here is that this problem is most basically a problem about energy conservation. So we are putting energy into the spring, that's elastic energy, and letting it go, and that's going to create kinetic energy of this whole cart assembly. Once it achieves that 12 feet per second, there's actually two kinds of kinetic energy that it has. It will have both a translational kinetic energy as well as rotational kinetic energy for the wheels, those front wheels, and so we need to account for both of those. In order to do that, I actually have over here some notes that I took. The total kinetic energy is going to be equal to 1/2 of the mass of the cart times the velocity of the cart squared, plus 1/2 of the moment of inertia, mass moment of inertia of the axle assembly times the rotational velocity of that axle. And to find that, the mass moment of inertia for that axle is just the mass of the axle times the radius of gyration. That's a common way of expressing another piece of information so that you can find this mass moment of inertia. Also, in order to find the angular speed of the axle once it gets up to the 12 feet per second, we would actually need to take the velocity of the cart and divide by the radius of the wheel, and that will give us that omega. Those should all be relatively review kind of concepts from a dynamics class. So we're going to implement all of this into this cell right here. All right, in this cell, we're going to say equals, and of course, half is just 0.5 times, okay, we need the mass now of the cart. And I didn't really want to belabor it, but I, over here, already have it converted from pounds into slugs. You basically just divide by 32.2 feet per second squared. That gives you a value in slugs. So I'm going to take and multiply by that mass of the cart, and then multiply this by the speed it ultimately gets to, which is, I'm going to put these in parentheses here, The speed that it gets to is this 12 feet per second. Okay, and that is then squared. Okay, now one thing to note here is that with just this amount of information put in there, since we're in feet and seconds and slugs, this is actually going to give us a value for energy that's going to be in force, which is pounds, and length, and that length is going to be in feet. I don't actually want that to be in foot-pounds, though. I'd rather have it in inch-pounds. So if I want this in inch-pounds, I need to multiply by 12 inches per foot, which I'll just tell you what, I'll put that right up here. Okay, so that first term I have there now accounts for the translational kinetic energy. And we're going to kind of ignore any rotational kinetic energy that we would have on these wheels. We're also going to kind of ignore that there might be moving parts here that might not all have exactly the same speed. We're just going to say close enough that all of it, we're going to count all of it as having a speed of 12 feet per second. All right. So now what we want to do is, you might notice over here on this page that we have now 1/2 of the moment of inertia of the axle. So what I want to do there is put in 0.5 times, and I'll tell you what, in the parentheses right here, I'm going to put in that inertia of the axle, and I'm going to actually come back to that. The next one that I want to do is take the angular velocity, and I'm going to square that. Okay, so now I need to fill in these two parentheses. For the first parenthesis, what we want to do is put in the mass of that axle assembly. Okay, so I'm going to put that in here. Okay, axle mass, all right, B18 right there. And then I'm going to take the radius and square it. Now here's where we get just a little bit of an interesting thing. Since we're doing energy here, and where it involves a conversion that involves slug feet per second in order to get a pounds force, I'm going to keep everything in feet for right now, and then I'll do another conversion to get it back to inches. So to get this into feet, what I will do is I'll take the number of inches for that radius of gyration and divide it by 12. Okay, and remember that calculation involved us squaring that value. Okay, now we need to go over here and take the fraction. You might remember from the our little thing right here that you take the velocity and divide by the radius of the wheel to figure out that angular velocity. So that's what I need to do here. The velocity of the cart, okay, and divide by, now down here I'm going to put in the radius of the wheel, and I have the same problem here that I want to put this in feet first, and so let me go ahead and put that in 5 inches divided by 12, and that gets me the value that I want there. But ultimately what comes out of here is a value that's in foot-pounds. And so the other thing that I need to do here is now do the same type of conversion that I did before with the first term and multiply this by 12. And I know that's a big old formula right there, but that should help us or get us the right answer in terms of the amount of kinetic energy. Okay, and that amount of kinetic energy that we need out of this cart once we've backed it up and let it go turns out to be about 234 or so inch-pounds. So now we want to fill in a few other things in the spreadsheet. One of them is a factor of safety at the solid height for the spring. Actually, these values that I'm putting in right here are standard values that are used for spring design, and so it basically recommends in the book to use a factor of safety of 1.2 when you're at the solid height. The end condition constant it talks about right here, this is for if a spring is going to be like this one where it doesn't have any support on the outside or the inside, it needs to not buckle, and there's an end condition constant that goes into that, and we're going to use a 0.5 because that's in one of the tables. As a matter of fact, I have that in this down here, table 10.2. Alpha ends up being 0.5. I'm getting ahead of myself just a little bit there. I'll talk about that a little bit more here in a few minutes. Okay. Next thing I want to do here is use a fractional overrun to closure of 0.15. That again is a kind of a standard value that it recommends not to ever be lower than that for most spring design. So we're going to take that as another one. Another one to use here is a shearing yield strength percent. Now here, this requires me to talk about this just a little bit. In order to maximize energy storage, it's actually helpful if you use a spring that has had its set removed. What that means basically is that the spring was made by making it originally a little bit longer than it really needed to be in its final form. But that's done so that a second manufacturing process could be done where you intentionally crunch the spring down and plastically yield it a little bit when you crunch it down to its solid length, and then when it comes back out, it achieves its final length that you were going for. This makes the spring stronger, and it actually allows us to use a different percentage here, and that percentage is 65%. Okay, and if you want to know where that comes from, there's a discussion in the book. I tell you what, I'll get to that here in just a few minutes. All right. Now, we want to try to design this spring to be the lowest cost possible. Okay. One of the tables that's in the book has a table in it that gives various strengths of various kinds of materials. And so I'm going to go ahead and enter these values here for the cheapest of the materials that's in that table. All right. And so the cheapest of those materials is a hard drawn wire, and it gives an A factor there of 140 KSI, an M factor of 0.19, and a specific relative cost of 1. Okay, so I'm just going to start with the cheapest one, or what seems to be the cheapest one, and try that one first. Now here's the thing. If it's not always cheaper to go with the cheapest material. There can be examples of where it might not be cheaper because you can use less of that material. So just make that little note at the very beginning. The next thing to note is that on table 10.5 there are various modulus of rigidity values, and that's something we're going to need for this material as well. And you'll see that for a hard drawn spring it actually has ranges of this value. And I'm just going to enter those here. 11.7. That is what it is for the smallest of the wires. That is valid up to a diameter of 0.32 inches. And then it goes up to 11.6. That's valid up to 0.64. Excuse me, that should be 0.064. Then it goes to 11.5, and that's valid up to 0.125. Okay, and then anything that's larger than that, we go to an 11.4. Okay, now I don't actually know at the very beginning what this what this modulus of rigidity value is going to be, because one of the things that we need to design is the wire diameter, and that's what this depends on. And so what I'm going to do here is, looking ahead just a little bit, we're going to assume that we know a wire diameter here. As a matter of fact, I'll go ahead and put that in. Let's just assume a 0.1 inch wire diameter as an initial guess. And if that's what we have, then you'll see that we should have an 11.5 modulus of rigidity. I'm doing this manually here. It's a little bit easier. I won't have to incorporate some sort of a fancy conditional function or anything in here to try to automatically select this. It also makes it to where the solution will be over a continuous domain. which that helps for a lot of solvers. And so I'm just going to do it this way, and when we get to the end of it, if it says that I have a if I have a wire diameter that is not what in the range that I selected here, then I can update it and then update the solution. So that's going to be the process that I choose there. Okay, in order to figure out what this lowest cost is, we're going to use an equation from the textbook that is, they call it figure of merit, but what they're really trying to get at there is, what's the lowest cost spring that we could make for this application. This is most important to do if you're talking about making large numbers of these parts. It's important to get the cost of each one as low as possible, and so we're going to try to do that here. All right, here's the equation for figure of merit. First thing you do is you take the specific relative cost. That's what's given in the table for material strengths. Okay, so I'm going to go ahead and let this equal that value. And you might notice here in the textbook it has this as a negative number. The only reason they put the negative out front is to cause this number to be oriented such that it increases when the value itself, when the absolute value of it increases. Well, they make that negative, then it makes that number bigger and bigger the cheaper and cheaper it gets. I don't think we need to do that. I think it's easy enough to understand that we're trying to minimize this value and that small numbers are good, and so I'm going to neglect the negative sign for this. All right, and then we're going to take this times a big numerator and divide by 4. If you go back and look at this equation right here, that's basically what it is. Now in the numerator we want to put pi. Okay, so inside of here I'll put pi. Now pi needs to be squared. Okay, and I'm going to take that and multiply it by the diameter, the wire diameter squared. Okay, so that's the next term right there. Wire diameter, I'm going to choose this value right here for the wire diameter. Okay, and then that needs to be squared. To this we're going to multiply, okay, n sub t. All right, n sub t is stored in a cell down here a little ways. Okay, that would be, well, it's actually not stored here, it's stored in active coils, which is right here. So what we need to do is actually put in here an equation that gives us the total coils from the active coils, and there is a table that's in the book that gives that to us. I believe it's 10.1, table 10.1. You take the number of active coils and you add 2, and I'll get into that here a little bit more in just a second. So now what we want to do is take this and multiply it by d. Okay, and d is right here with mean coil diameter, which that makes that a little bit hard for me to find, but I'll get it by doing that. That's my mean coil diameter, and I believe that should be my entire equation in that cell. Now it's probably not going to like it just yet because I haven't loaded all my initial guesses for all of these values into the cells that are going to actually be solved for with this spreadsheet. So let me do that. I'm going to put in a 1-inch mean coil diameter here. Let me start with I'm just putting in some numbers that I feel like might be close. There's not a big science to picking these, but this is just kind of guessing. We'll put in a free length of 8 inches and a maximum force of 80 pounds. Okay. Now if you're interested, we can also fill in these cells over here. I'll tell you what, I'm going to save that for just a minute from now because we don't necessarily need those right away. What I want to get into is the actual process of trying to optimize this problem. All right, and that involves dealing with all of these cells down here. And this is kind of the crux of the problem. So what we're going to do with these is we're going to set up a number of constraints. Those can be equalities, they can be inequalities, and these are the ones that I'm going to fill in here. The first one involves taking the spring constant, which I have stored right here. Okay, so I'm going to say equals that spring constant. Okay, and that is going to be equal to the spring constant equation, and that's given right here. It's going to be d to the fourth g over 8d cubed na. Okay. So this here will then be the wire diameter. Okay, I tell you what, this is most basically a fraction, right? So a lot of times I load that in first. So we'll put in this to the fourth, okay, times. Then in here we want to put in the modulus of rigidity, and we're just going to put in the modulus that we were using right here, but we do need to also multiply by, since this is given in MPSI, to make it proper we need to actually multiply by 10 to the 6th. Okay, and I believe that takes care of my numerator. The denominator should be 8d cubed na. Okay, so here 8 times d cubed. Okay, so this is the capital D, so we're using mean coil diameter, times Na, and that is the active coils. Okay, and I believe that takes care of my spring constant equation, and since I'm using all base units here, I believe it does come out in inches or pounds per inch, which is good because that's what we want. All right, so that puts in this value here. And you'll notice these don't equal each other right now. And they don't equal each other because you haven't actually done the solution yet. All right, so this is the spring constant we guessed. This is the spring constant that's being calculated based on the other parameters that are in the solution set, basically right there. All right, the next one we want to do, this is one of the more tricky ones because it doesn't give you a lot of guidance in this text on how to design a spring if you're doing it with the set removed as opposed to doing it without the set removed. Most of the examples that they give there in the text and the ones that I've done in class so far, we've assumed that the set was not removed. When the set is removed, the only place it really gives you the equations to deal with that is in figure 10.3. And these are the equations that it gives. All right, it tells you that, first of all, the yielding strength in shear can be calculated using 0.65 of, times this A over D to the M. And so we can just put that in for the shearing strength, all right? But then that goes in right here and it calculates, this is basically a stress-based equation to calculate diameter. They have it solved for mean coil diameter. So basically what we need to do here is in this cell, we're just going to put in that mean coil diameter. Okay, so equals that. And here we are going to do a pretty big calculation. Okay, again, most basically it's a fraction. Okay, and in the numerator, first parentheses that I'll put in here, this is going to be everything that we need to calculate that S sub SY, the yielding strength in shear. Okay, and so this is just going to be equal to, and remember I used this shearing yield strength percent. This is so you can change it later if you want to. So I'll just go ahead and reference that. Okay, multiplied by this A value. All right, now something to keep in mind, I'm going to try to keep all this in base units, and this was in KSI. So I'm actually going to take this and multiply it by 1,000 to get it into PSI. Okay, and then all of this is going to be divided by, okay, inside of these parentheses, we are going to put the diameter, the wire diameter, all right, and that will be raised to the exponent. Okay, and the exponent is given right here. That's this m value. All right, so that much should give me the strength value. All right. What's next here in this equation, after putting in the strength, so basically I put in all of this stuff just now, and what's next is I have to put in a pi and a d cubed. Okay. And then d is over here. This is the mean coil diameter again, cubed. And in the denominator, I need to put 8 times the factor of safety against yielding when it's at its solid height. That's that n sub s. Okay, so I'll go over here, 8 times the factor of safety. Okay, times, in the parentheses here, I'll put in a 1 plus the fractional overrun to closure. And then all of this is going to be multiplied by the maximum force that the spring has to carry when it's at its maximum expected working compression, the amount of, deflection. Okay, let's make sure that we've got all of those in there correctly. So now that we have that equation entered properly there, we just go ahead and hit enter, and that gives us our coil diameter. Okay, and again, you'll notice that it's different than the coil diameter I have, or that was the initial guess, but that's completely fine. That's one of the things it's going to solve for. All right, so the next one we're going to do is an equation that we basically are going to come up with solid length, but we're going to come at it from two different directions, because you'll notice that solid length was not one of the parameters that we had for our list up here. Okay, so we need to do this kind of two different ways. The first way comes from table 10.1, and so we can look that up over here. Okay, basically what this does is it figures out what the height of the stack of the wire is when it's closed all the way. Okay, and you just take the diameter of the wire times the total number of coils. Okay, so that part is relatively simple. We just say wire diameter times the total number of coils, and that is just going to be equal to the number of active coils. Number of active coils here plus 2, based on table 10.1. Okay, so that's the height of the stack. The other way we have to come about this, let me talk through that just a little bit. You'll notice here there's several other equations. So equation 1017 is where the book starts to talk about what this fractional of overrun to closure is. That's that xi term right there. We also know that Hooke's law applies right at the point where the spring goes solid. We also know that the definition of how much deflection there is when it's solid is just the free length minus the length when it is solid. We can take those three equations and put them together into an equation that looks like this. And so that's what we need to enter here, because this is another equation that gives us the solid length of the spring, but it does it in terms of the other variables that we already have on our sheet. Okay, so basically equals the free length, which is right here, minus, and again this is just going to be a fraction, and in the first part of that fraction we are going to have 1 plus your fractional overrun to closure. Okay, and actually this should probably be put in parentheses. Okay, 1 plus the fractional overrun to closure, which is right up here. Okay, and that needs to be multiplied by the amount of maximum force that we have here. Okay, and then this should be taken divided by our spring constant, which is right here. Okay. So that's how we basically have a cell here that's one way of getting your solid length, and we're setting that equal to this other way of getting your solid length. All right. And essentially, that's how we're going to incorporate this idea of how long the spring might end up being. It's kind of how we get free length involved in the equations for this system. The other way that free length is involved is we need for this spring to be stable. You might remember it's not in a hole, it's not wound around a rod, and we need it to be stable against it buckling. And it gives a way to find that in here. So basically what we're going to do is set this cell equal to the free length. And then this cell, the stability condition, is given with equation 1013. And I have that in here as well. Equation 1013 says that if you're dealing with a steel spring, which we are, then your free length needs to be less than, can kind of be less than or equal to, but less than 2.63 times the coil diameter divided by this end support condition alpha. Okay, and since we have squared and ground ends, we have a table that tells us that that alpha value is going to be equal to 0.5. Okay, so we'll put that in here. This is going to be 2.63 times your mean coil diameter divided by alpha. Okay, and alpha was up here. All right, and that gives us one of the constraints that we have to meet. Now the thing is, as long as you're stable, you're happy, and so you might notice this is a different kind of a condition that we have employed here relative to the other ones that we've seen so far. All right, we're almost done, believe it or not. What we need to do now is put in an equation for elastic energy. All right, elastic energy, the classic equation for this is 1/2 times the spring constant times the amount of deflection squared. Now here's the thing, we also know Hooke's law applies, right? So that tells you F equals K delta. Well, if you rearrange F equal K delta to be delta equal F over K, and then plug that delta back into the delta we had for elastic energy, it allows you to solve and get 1/2 of your F squared over K. All right, this is another expression for the amount of elastic energy stored in a spring. And that's the one I want to use because force is one of the elements that I have in my solution set. The stuff here in blue is basically going to be the stuff that Excel tries to vary in order to meet all of these constraints that I'm setting up. Okay, so 1/2 F squared over K. All right, F is here, and I'm going to divide that by my spring constant. All right, so we're going to hit enter here, and that gives us how much elastic energy we have stored in the spring. Okay, well, the thing is that elastic energy is going to be equal to the kinetic energy we computed before. Okay, so what we have now is that we've set up all of our constraint equations, and we have the variables that we're trying to solve for. So what we need to do now is use the solver that's built into Excel to try to optimize this situation. The way this works is we're trying to minimize this figure of merit by changing these variables right here so that they meet all of these constraints, and while they do that, minimize that function. The nice thing about Excel is it's got that ability built right into it. I want to show you how to use it. There's a little button right here that says Solver. Okay, if you pull that up, okay, it looks like I thought it was going to get rid of this whenever I restarted Excel, but it didn't. So let me show you what you do. So it has this target cell that is, it says B28. That is basically the cell that it's trying to optimize. okay? And it says we're trying to minimize it. So it says, that's the next step right here, is that we're trying to minimize that cell. And it says we're going to do that by changing, okay, right here it says cells B30 through B35, right? So if you wanted to update that, right, what that looks like is you just go over here and select those cells, okay? It's pretty much that simple. And I'll delete this equation. All right. Tell you what, I'll delete the last two, and I'll show you how I put them in there. So we're going to add this one right here. So we're going to say that the free length has to be less than, it says that's less than or equal to, that's okay. That's actually probably a more appropriate way to express that one anyway. And then here we're going to put in this value, okay? And that adds that equation. Now we can add another one. We can put in this reference, only we're not going to make it less than or equal to, we're going to make it equal to this other constraint. All right? So that should be relatively simple to understand how to put in those constraints. And once you put in those constraints, you just hit solve. All right? And really good, it says solver found a solution, all constraints and optimality equations or conditions are satisfied. Okay? And at this point, if you want to, you can keep the solver solution, which that's what I'm going to do here. I'm going to keep that solution. You see here it found a wire diameter, a mean coil diameter, number of active coils, a spring constant, a free length, maximum force, and it did that while making these values here meet each other. All right, and you'll notice here, even though we applied a less than or equal to constraint here, it actually did make them equal to. And what you can take out of that is that you're probably optimally set up this spring if you don't make the diameter big, the mean coil diameter bigger than it has to be in order to meet that stability constraint. Okay? Tell you what, we'll put in the last few things here. To find inner diameter, all you do is you take the mean coil diameter, which is this right here, and you subtract the wire diameter. All right. If you want to find the outer diameter, you take the mean coil diameter and add one wire diameter. Okay, so if you want those, you can get those. We talked about this a lot, but if you want the total coils, you can take the active coils plus 2. Again, that's from table 10.1. Spring index, this is sometimes something that we like to know about. So spring index is just mean coil diameter divided by the wire diameter, which I believe that's equation 1 in the text. Okay, and in case you're interested about this, it does give you some guidelines for what that spring index should be. I believe it's 4 to 12 might be what it says. Anyway, it looks like we are well within our range of acceptability for the spring index. Now pitch, this one's a little more interesting here. We don't talk about this a lot, but it's interesting to note pitch is basically how far it is between each coil. And so what we're going to do here is use another equation that we had from table 10.1. It's just the free length minus 2 wire diameters. Okay, so the free length minus 2 wire diameters. All right, and divide that by the number of active coils. Okay, and that just tells us how far it is between each coil. That's sometimes an interesting thing to know, and that's when it has no load applied to it. All right, the next thing to look at is the solid force. Okay, that's how much force is in the spring at the moment it goes solid. Okay, and this you just use Hooke's law. We already know the spring constant. Okay, you just take that and you multiply by the deflection at that height, and the deflection, we looked at this earlier, is just equal to free length minus solid length. and the solid length, I believe, was down here. Okay, so you see there, it actually can, the force can get a little bit higher there in the spring as you continue to push it all the way to solid. This is because of that fractional overrun to closure. We decided intentionally not to let it go all the way solid. All right, so that's the solver. What we've come up with now is this figure of merit. Okay, that figure of merit is what we are trying to minimize, and so it appears as if we have come up with a number there that has been minimized according to getting all these values to some level. What we want to do next is go ahead and see how that might compare with some of our other choices. Okay, so I've already set up another couple of tabs here. So this tab, I changed it up a little bit for the case of oil quenched and tempered wire, which is another type of steel wire. And I have it loaded. It's a similar, very similar kind of sheet. The only things that I've changed are it has different values to find its strength, as well as it does have a different specific relative cost. The other thing it has is that the modulus of rigidity, how it has it listed in table 10.5, this one does not have a variable modulus of rigidity, at least not as reported in that table. So we just put in the value that is reported in the table of 11.2 and let that be what it is. Okay, so now I think it's essentially all set up, and all we've got to do is just run the same kind of a solver again. All right, so we solve it, and I'm going to say keep that solver solution. And you might notice here that this relative cost is a little bit larger, but you might also notice that the wire diameter is a little bit smaller. All right, and as is, I believe, the mean coil diameter. If I go back over here, yeah, the mean coil diameter for my first solution was a little bit larger. So you can get some advantage in terms of space savings, but the cost is going to be a little bit higher. In our case, we're just trying to minimize the cost, and so we don't necessarily care about spatial constraints for this particular problem, and so we're just going to let this kind of speak for itself that the hard-drawn wire is a better solution. Okay. Oh, I forgot to do one thing over here for the hard-drawn wire. I knew I was going to forget if I didn't come back to it. This wire diameter solution that came out might be different than what I thought it would be whenever I set my modulus of rigidity. Okay, and so what you notice here is with 0.155 as this wire diameter, I need to change from 11.5 because that's only good up to 0.125 inches of diameter. So I need to change this down to 11.4. Okay, and run it again. Okay, because if I don't run it again, it won't update these values. And so if I go back to the solver, everything should still be set up in there the way it should be, and you hit solve, and it actually makes it even a little bit more cost effective by dropping that value down just a little bit. Although you will notice we don't have quite as much difference now for mean coil diameter between this solution and the oil quenched and tempered solution that I have here. As a matter of fact, it looks like this one may, yeah, it is still more compact. It's just, anyway. All right, well, the last one that we need to consider is music wire. All right, so music wire kind of did the same thing. I assumed the modulus of rigidity. By the way, music wire does have this variable modulus of rigidity. It's not extremely variable, but it's a little bit variable, and so I'll set that up in the same way. It does have different values for strength here, but I'll just go ahead and run the solver. When I hit solve, okay, I'm going to keep that solver solution. You'll notice that it came up with a smaller wire diameter as well as a smaller mean coil diameter. Okay, so having the stronger material does save space, as you might expect it would. But the higher relative specific cost, which is basically like how much does it cost per unit of volume of the material, is so much higher that the cost is actually higher as well. All right. So this is not as cost-effective a solution as the hard-drawn wire we had just a moment ago. All right, but this value for the diameter, 0.144, means that we're again outside of this range. I need to change this. Instead of 11.75, I'll change it to 11.6. And it's not like sometimes when you use Excel where everything else automatically updates. With this solver, you actually do have to run the solver again in order to get all the cells to update. Okay, and that's how we get our final figure of merit. All right, so music wire, 2.11, oil quenched and tempered, 1.64, and hard drawn wire, 1.40. And so our solution here that we would accept is that we would wind a hard drawn wire according to these parameters that we put in right here, and that would be our most cost-effective spring to drive the cart in this way. I hope this has been an interesting and helpful presentation of this, and appreciate you watching. I hope to see you on the next one.